Thanks a lot. It's a pleasure for me being here. And as you mentioned already, it's all about bioreactors and how we can enable the biological transformation. But before I start with this topic, please give me a chance to introduce myself and the company I'm working for. So I'm responsible for research and innovation at Festo, which is a family-owned company in Germany with about 22,000 employees. And we actually right now sell and produce and develop products in the field of industrial automation and factory and process automation. So what you see here, first of all, seems that it has nothing to do with bioreactors. So you see gantries and pneumatical drives and motors and control technology and all the things that is used in the daily production of our daily lives. And within the company, we have established a so-called bionic learning network. And over the last 20 years, we have learned from nature together with university partners worldwide and have developed more than 50 prototypes, mainly robotics, soft robotics, flying objects, underwater objects. And with these future concepts, actually, we want to fascinate people for technology. We want to learn from nature and we want to enhance our product pre-development. And as a very short introduction into this activity, I show one video with some highlights before I then finally go into bioreactors. So having experience in bionics and robotics over the last year, we decided that we now want to take this knowledge actually and try to solve real problems. Therefore, as you all know, one of the biggest problems is the global warming due to the fact that we have a lack of sustainable and circular processes and still need that much oil-based materials, leaving a big CO2 footprint. And just some numbers, in the last year, we used more than 4.2 billion tons of oil as humans, most of it for transport, heating and energy production. And there might be solutions to get rid of oil using renewable energies, for example, or the batteries we've heard yesterday, but still we need more than 7% of the oil just for plastics. And take into account that if we burn 1 ton of plastic, which we usually do at the end of life, releases 3 tons of CO2. So in total, almost 1 billion tons CO2 each year. And this is all CO2 that was captured by photosynthesis millions of years ago. And for those who forgot what we all have learned in school once, photosynthesis is just what plants do, taking carbon dioxide and water with the energy of light and producing biomass and oxygen out of that. And this is what I want to talk about, how we can use the automation technology for a higher CO2 fixation. And land plants, for example, they can fixate approximately 1 kg a square meter. Algae is already 10 times more efficient. And if we grow the algae in the bioreactor, like you see it here on the left side, we can increase the efficiency again more than 10 times. So it's more than 100 times more efficient as land plants. And while doing so, we produce 7 times more biomass and using only 0.55% of water. So in this short video, I will explain what we have developed over the last 2 years. So actually, these are two kinds of bioreactors, a small one and a bigger one. And the most essential part actually is the tank where all the organisms grow. And it's all about how to make this growing process as efficient as possible. Because biological processes are much slower than chemical processes, and we need to increase the efficiency using control devices, using a lot of sensor, controlling all the parameters like temperature, pH, feeding of CO2. And also we have used a quantum sensor developed from a startup together with us, where we really can detect the size and also the health conditions of the single cells using microfluidics and mass flow controllers in this case. And all these sensor data actually and the control algorithms are stored in the software. We use augmented reality for an easy operation. And the main purpose actually is to bring our automation technology to scale up and to make the process energy efficient and grow as efficient as possible the algae. And therefore we also pump up the fluid into a collector to increase the surface to catch the light, or to collect heat or absorb heat depending on the weather conditions. And in the small reactor that we have developed in parallel, we can even improve the algorithms much quicker and easier because we are working on a smaller laboratory scale. And together with the Max Planck Institute, we think about how we can optimize the process on the cell level itself. So we're working with living material, and I mentioned already that algae can fixate CO2 much more efficient than land plants, but there's also the potential to generate a lot of materials. So actually everything that is today produced out from oil can also done in a biological process, like food, bioplastics, cosmetics, drugs, fertilizers, everything in the end can be produced by algae. And this could be a very cost-efficient and sustainable process because it needs less temperature, less pressure, and the products we get out of these biological processes are much easier to bring back in the natural circular economy at the end of life. So it's all about getting rid of the oil and replacing the conventional materials. I mentioned algae. Here you see bioplastics that we got out of it, which we can 3D print. We got already color out of it, which you can use in food, for example. A big market is animal food because cows release less methane if you feed them with algae. And in the end, we want to get rid of fossil resources and don't want to release additional CO2. So what is the next step actually? What you have seen now is a laboratory scale actually and a demonstrator that we have showed on many places already. But now we are working on how to scale it up. And therefore we partner with other companies. In this case, you see an image of Algoliner that has developed a solution how they can very efficient produce really long tubes with thousands of liters of water and algae in it. We further want to optimize the process, collecting the data right now using our AI algorithms. We think about how can we combine these kind of bioreactors with other technologies like CO2 capturing machines or biogas devices. How can we harvest the algae in a more efficient way? And Right now we work with algae, but you also can expand it to other organisms like E. coli, bacteria, for example, to produce tensides or other material we want to have. So remember the one number I mentioned in the beginning. So all plastic fixes around almost 1 billion tons of CO2. So our question was, how many bioreactors do we need to build actually to get rid of this and at least get the CO2 equivalent? So one tube system, as I just have shown on the image, can grow about 6,000 tons of algae a year per square meter. A ton of algae can fix 1.8 tons of CO2. And if we want to fixate all the CO2 resulting of plastic in 1 year, we would cover a surface of 48,000 square kilometers in the tube system, which corresponds to about 1% of the area of the Sahara. And this is a conservative approach. We're quite sure that we have the potential to increase the efficiency by a factor 10. Then it's 0.1%, and this is 5 times London. So I personally think it's still a very huge surface, but it seems somehow reasonable. And we are not the only ones working on this topic. So there are many companies working on that. But for us, I think we really can help to bring it from a laboratory style to an industrial production, so that in the end we replace chemical processes with biological processes and therefore contribute to CO2 neutrality and circular economy. So thanks a lot, and hope to succeed.